So, as Dave mentioned, my name is Sinickas. That's true. Since September, I've been working with Dr. Bruce and these six fine people, seven if you count Max, and I've been looking at extreme avalanches. Is that got it? I've been looking at extreme avalanches and statistical estimation of them. But before I get into that, I'd like to give a bit of a background on myself because I am fairly new in this patch. So I started out at Melbourne University. I received civil engineering and economics and finance degrees. I worked as a structural engineer for a while, but I really wanted to spend more time outside, so I skipped the Tasman to New Zealand, where I worked at a place called Temple Basin, and I was first introduced to snow avalanche science. I really wanted to learn more. I travelled to Lake Louise and took a job as a ski patroller, mostly to work on my biceps, but also to try and understand how they manage avalanche risk in terms of skiers. And as I learned more, I became really fascinated with this idea of the extreme or really big avalanche that falls over trees and damages infrastructure and the sort of planning and engineering side of everything. So examples of those from just this year alone would be the Savoie avalanche in France in March, Pakistan avalanche in April, and the Kosovo and King Cove, Alaska avalanches in February. So when Bruce posted a position for a graduate student to study extreme avalanches, I jumped at the chance. A lot of my field work will be in the summer, and we haven't had one yet, so I don't have a lot to tell you in terms of results, but I can go through what I'd like to study, how I plan on studying it, when I plan on studying it, and how I hope that it will be relevant to you. I'm really keen to hear any feedback, so questions and comments will be most welcome at the end. So I'm looking at statistical estimation of avalanche runout. And under this, I want to address two topics. Number one, the relationship between frequency of avalanches and runout distance. And number two, looking at the effectiveness or the errors of digital tools such as Google Earth or digital elevation models, which are essentially 3D maps of terrain, and see how good they are at estimating runouts. Before I get launched into these topics, I'd like to present three tidbits of information just so that we're on the level. And this is the interactive part, so could you all please stand up? So for this exercise, I don't want you to cave into peer pressure. I'm going to present a timeline with increasing return periods. When you feel that an avalanche with that return period has become extreme, I'd like you to sit down. So here's a test. If there's an avalanche path and a road at the bottom of it, and an avalanche hits that road daily, and you think that that is extreme, please sit down. Great. Great. What if that avalanche hit the road weekly? Monthly? Yearly? Every 5 years. Good. Every 10 years. Great. Every 20? Every 30? Every 100? Uh-oh. Every 300. Okay. So as you can see, the idea of the extreme avalanche is quite variable. I've tried this test on lots of different people. My ski patroller friends often choose sort of lower return periods around yearly, 5-yearly. And my engineering friends who don't know anything about avalanches often choose sort of 30 to 100 years. So who's right? I think it entirely depends on context. In this case, for this presentation, and it seems for avalanche engineering and planning as a whole, the return period of around 25 years plus would be it. Bit number 2. So why are we all standing here listening to some nerd rattle on about statistics when if you wanted to find the extreme runout position of your avalanche, the first thing you would do would be to ask the local, and then you'd probably have a look at some historical records, and most importantly, you would head out to site and have a look at vegetation damage. And that's true. But what if your path is in an alpine? Or your path runs down onto a lake across country trails? Or I think this is the protection. So there's two options available. There's two options available to us here. Actually, there's lots, but two of the options would be to run a dynamic model, which would take inputs such as the amount of snow that's available to slide, the roughness of the terrain shape, and it would spit out an estimate of the runout position and a whole lot of other things like velocity and deposit height. But sometimes these inputs are tricky to estimate, and so statistical models are used instead. Two statistical models that you might have heard of through the mapping courses and in general would be the alpha beta and the runout ratio. And I'll get on to that next. Oh, so if you were back at school and your professor or your teacher said that you were going to be focusing on probability and statistics for the next couple of slides, your face would probably look something like this. But I don't think that it needs to be a Hitchcockian experience. I'm going to go through statistics and probability at a very high level in terms of avalanches, and it's intended to be a review. I don't want to patronize anyone, so if you think I'm going too slowly, feel free to groan loudly or hiss something and I'll take the hint. So this is how a statistical model theoretically works. So if we were trying to find the runout of this path here, a statistical model could tell us what the extreme runout was based on the extreme runouts of a whole bunch of other paths in the range, the same amount of range. It's not me. Should I stand somewhere else? All right. Okay. So I like to think of it as a peer pressure model. Because basically what you're doing is trying to determine how far your avalanche will run based on what every other avalanche did. But it's not quite that simple. Some paths are short, some are tall, some are shallow, and some are steep. So you can't just take the average runout from the range and apply it to your path. You have to be a little more clever than that. So some really clever people came up with this idea. This is the avalanche. You can relate the alpha point, or the extreme runout position, with the point where big avalanches tend to slow down, or the point where the slope transitions to 10 degrees, also known as the beta point. And there are equations that represent the relationship between alpha and beta for a number of different ranges in Canada. For those of you that had seen Catherine Johnston's presentations, she was looking at this relationship for the Columbia and the Lizard ranges. So this is a really cool model because it gives you an idea of the extreme, or the 1 in 25 year plus avalanche runout position. But what about the 1 in 5, or the 1 in 10, 1 in 15? So in response, Dr. David McClung, who's sitting right here, published a really interesting paper that relates, well, that answers this problem. And what he proposed, and I really hope I haven't said anything correct. Okay. So he proposed that you can use statistics to relate these two ideas. So this is the path that we were trying to find before. It's just a front shot. And from first inspection, you can see maybe 2 trim lines, and I'm sure they're a bit different and there might be more or less when you actually get out there. What we know is that as you walk down the avalanche path, or in other words, as the runout distance increases, so too does the return period. And what Dr. McClung proposed is that you can model runout distance using a Gumbel distribution and a return period using the Poisson distribution. This is really cool because all you need is a return period at this, or at the beta point, wherever it is on this path, and the model will spit out estimates of the return period at different distances past the beta point. Could be super useful for avalanche planning. What's wrong with it? Absolutely nothing. It just needs to be validated. So what I would like to do is try to work out where this model works, where it doesn't, and what the uncertainties are associated with it. And I want to do it by looking at 40 avalanche paths and recording the return periods along them and matching them with what the model spits out. I want to do this, it's quite ambitious, but I'd like to do most of these paths in the coming summer. And I've got time in the next summer, just in case that doesn't follow through. And I hope that this will be really useful for avalanche planning and engineering purposes. On to topic number 2. So it seems that these days there's been this explosion of accessibility to technology. Everyone seems to have a smartphone and there's apps for this and apps for that. The avalanche industry obviously is no exception. I don't think that for statistical estimation, anything will ever get rid of the need to have your head in the orbit. But these tools could be really useful. Google Earth is one obvious one. People use that for terrain familiarization. It's got lots of imagery on it to look at trim lines. And the other one, if there are any GIS users out there, is digital elevation models, which are these 3D maps of terrain. They could be really useful because they would speed up the processes that you have to go through before you get to site. And if you don't want them to speed up, you could improve the quality of the processes that you do before you get to site. What's wrong with this? Nothing, but these new technologies are just representations of the Earth. And as such, they have inherent errors, and we need to find out where they are. So again, I want to compare beta points that I found in the field with those that are predicted by 2 DEMs, digital elevation models with different resolutions, and Google Earth. I'd like to do this in the summer, and I hope to be able to come up with some minimum accuracy requirements for using these models as tools for statistical estimation. So I took some data kindly provided by Catherine Johnston from last year. These are 3 paths that run from Mount Fernie. Fernie is over here somewhere. So the center line of the path is shown in green. And these blue pixels here, sort of in the bottom right-hand side of the sheet, are areas on the ground where the model predicts the slope is less than 10 degrees. So theoretically, the beta point is the point where the center line first touches one of these blue spots. I'm going to zoom in here. So you can see 4 dots. The green dot is what was collected of the beta point in the field. And so we're taking that as the true beta point. This data was collected using a GPS with an accuracy of plus or minus 7 meters. So it's not exactly true. And for my work, I'll be using a GPS of plus or minus centimeter accuracy. And then we have the three estimated beta points. We have Google up here. We have a digital elevation model with a 23-meter grid. So that means there's an elevation point every 23 meters square. That's down here. And then even further down, we have a digital elevation model, 30 meters, a little bit further along. Now, there were only 11 paths that I had data for, but from these 11, I found that on average, the digital tools, so the Google Earth and the 2 DEMs, predicted the beta point to be within 10 to 200 meters of where it actually was. This sounds pretty cool. Except that when you plug it into the model, that results in a 400 meters of inaccuracy, which I don't know about you, but I wouldn't want to be putting my house in with that line if it was 400 meters out. So from this, I've had a stab at the required accuracy. I think we need probably about a 5-meter resolution and a 10-meter vertical accuracy so that the model predicted beta point is within 50 meters of where it actually is. I'm hoping that that 5-meter resolution will increase with the number of paths that I survey, but we'll see next year. So to sum up, I'd like to look at 2 aspects of runout modelling. The first would be to validate Dr. McClelland's model. And the second would be to look at the errors associated with using digital tools for determining beta points and then using them in statistical models. I'd like to do this by comparing field observations of return periods along a path and beta points to those that are spat out by the models. I plan to do it over the coming summers. And I hope that in the first case, it provides a good tool that you can have confidence in using for avalanche planning and engineering. And secondly, minimum accuracy requirements in terms of resolution and vertical accuracy. So thank you to all our sponsors. We really appreciate your support. And yeah, comments and questions.